Hello everyone, my name is Minli Liao. Today I'm going to present our work that's a deep technical review of the nZDC fault tolerance scheme. First, let me explain what is nZDC. nZDC is a software-based fault tolerance scheme from Arizona State University, first published in DAC 2016. Basically, it is a compiler scheme so that when a program is compiled with the nZDC compiler, the resulting binary will be able to detect errors when running on faulty hardware. Note that nZDC is an error detection scheme, so there are only mechanisms to detect and alert about the error, but there are no mechanisms to correct the error. nZDC achieves error detection through instruction duplication, where instructions are duplicated to generate a redundant execution. And instead of using the same registers in the redundant execution as the original, shadow registers are used in the redundant execution so that the results from the original execution stored in the original registers can then be compared with the results from the redundant execution stored in the shadow registers. If the values in the original and the shadow registers are not equal, this indicates that an error has occurred. The comparison is done on all registers for a thorough check, not just the destination registers. And in nZDC, this thorough check is usually inserted before a function call. And also, there is an error handling block that is inserted at the end of each function. This is where the execution would branch to when an error is detected, and users can insert whatever code they want to handle the error when it is detected. Of course, to make sure that the original and shadow registers have the same value after calculations, the shadow registers would also need to be set up with the same value as the original registers to begin with. This initial setup is done at the beginning of the main function in nZDC, and values are copied to shadow registers again after a function call. This is because the return register cannot be duplicated without modifying the calling convention. Up to here, what I have described is similar to other techniques using instruction duplication. Next, I will talk about the improved and new features that are distinct to nZDC. One such feature is the input parameter error detection. In nZDC, shadow registers are not set up at the beginning of a function except for the main function. This is because if there were copies and an error were to happen after the check before the function call, but before the value is copied in the beginning of the function call, then that error would have propagated to the shadow registers as well. By removing the copy in functions other than main, we ensure that we can detect any errors on the input parameters. Another new and improved feature of nZDC is checking for stores. Previous techniques only check for the register values for stores before the store, because stores cannot be checked through duplication. However, this leaves the program vulnerable since stores can still have errors after the check but before the store or during the store itself. nZDC, on the other hand, checks for stores through introducing a checking load, where the stored value is loaded back to check for errors after the store. Note that the stored value is loaded back to the original register instead of the shadow register. This means that any errors that would happen on the original register is not propagated to the shadow register. Hence, it is possible to detect errors by comparing the values in the original and shadow registers. With this checking load, nZDC is also able to detect errors that happen in the store queue, for example, which was impossible with prior techniques. The last distinct feature of nZDC I'm going to talk about is checking for conditional branches. nZDC is capable of checking for errors in both the branch direction as well as branch target of conditional branches. This is a bit complicated, so I will explain it step by step. Conditional branches are taken or not taken based on the value of condition flags, and the compare instruction is usually used to set up that flag. First, this compare instruction is substituted with the subs instruction, where the result of the subtraction is recorded in an additional register called CDR. This is possible because the subs instruction also sets up the condition flag in addition to performing a subtraction, and the compare instruction is actually just a special case of subs where the subtraction result is discarded. Then the subs instruction is duplicated using shadow registers as its source operands, and with the result of subtraction recorded in yet another additional register called CCR. While the subs instruction and the subtraction result can be duplicated, the condition flags cannot. Hence, the result of the condition flag from the first subs instruction is recorded through another conditional instruction, where the value of CDR is bitwise inverted based on the condition flag result. If we take the taken path as an example, where the values of x1 and x2 are equal, then the value in CDR should be bitwise inverted from the subtraction result. Then in the branch taken block, the value from CCR and CDR are XNORed together to check for branch direction correctness. If there are no errors, the CDR value should now be the inversion of CCR, and the XNOR operation should result in 0. To check if the branch target is correct, nZDC uses static signatures for branch target blocks. The signature is then XORed onto the CDR before the branch, and then in the target block, this is XORed onto the CDR again to revert its value. If there were an error in the branch target, the CDR value would not be reverted, and the XNOR operation would not result in 0. The operations on the not taken side is similar, with conditional inversion checking for branch direction correctness, and static signatures checking for branch target correctness. Now that I have explained what nZDC is, let me talk about the problems we have found when trying to use it. We were very happy to find the open-source implementation of nZDC uploaded by the original authors on GitHub for the ARMv8 AArch64 architecture, and we were trying to apply it to the commonly used spec and parsec benchmarks to get performance results. However, to our surprise, the nZDC implementation could not even successfully compile these benchmarks, and even after fixing a list of errors that prevented compilation, the resulting binaries could not even complete error-free runs. By error-free, I mean that even when running our error-free hardware, the binaries could not complete the execution. It would either crash or report false positives as errors. Upon taking a closer look at the nZDC implementation, we have identified several more significant problems of nZDC that are related to its new features. One of the significant problems is the lack of consideration to the load-store asymmetry. Recall that nZDC checks stores by loading the stored value back. In this example, the 64 bits of the x1 register is stored and then loaded back, and the assumption is that loads and stores are symmetrical, so whatever was written to the memory should have been loaded back. Unless there's an error, the register value should remain unchanged. However, let's look at the following case where only part of the register is stored. Here, the W1 register refers to only the lower 32 bits of the X1 register. Hence, only the lower 32 bits are stored to the memory. Now, when we load the lower 32 bits back, does the X1 register value stay unchanged? What happens to the higher 32 bits? Well, in fact, the load would sign or zero extend the loaded bits to fill the entire register size, overwriting the higher bits of the register. Note that this doesn't only affect the 32-bit case, but checking loads of any sub-register size stores such as store byte would also suffer from the same problem. Then eventually, when we compare the values of x1 with its shadow copy to determine if there were an error, the value from the original and shadow register would not differ, causing nZDC to signal error detected, even though the store itself was completely error-free. Note that this is more severe problem than a mere false positive, because even if we ignore the comparison result, the execution would still end up in error when the higher bits of the x1 register is used. Another problem we have found is related to the conditional branch checking. First, there was no implementation of it at all in the open source repository. However, this does not explain why the binaries could not finish execution. Even without the transformation, conditional branches themselves should not fail, right? Well, we have found that the problem is related to an edge case of conditional branches where the instruction used to set up the condition flag is also preserving its result. Here, instead of using the compare instruction that discards the subtraction result, the original code already uses the subs instruction and writes back the subtraction result to the x1 register. Due to the lack of conditional branch checking, the flag setting instruction was never duplicated, which means that when the XY register value is eventually compared to its shadow, nZDC would report this as an error even when there wasn't anything wrong. Note that we are calling this case an edge case simply because the vast majority of conditional branches uses the compare instruction. However, this edge case is not that rare either, because we have found at least one occurrence of it in most of the benchmarks we have tested. Now, what if we had the conditional branch checking transformation in there, and the conditional flag setting instructions are duplicated? Would it have worked directly unchanged on this edge case? Well, XY and shadow would now have values that match, but since the CDR and CCR registers were used to store the subtraction result, XY and its shadow would not have the correct value in them. This means that actually, for the transformation to work, the result of subtraction in CDR and CCR would also need to be copied to the original destination, that's XY and its shadow. Note that this edge case, where the subtraction result is preserved, is actually a more general case, where the compare instruction is actually just a special case. This means that while nZDC have worked for the most common case, it has disregarded the more general case. The last problem is actually more widespread in nZDC, and that is the lack of consideration to the library and calling convention compatibilities. This is generally related to setting up the shadow registers by copying the values from original registers. Recall that nZDC first sets up the shadow registers in the beginning of the main function, but no longer copy registers at the beginning of other functions to avoid input parameter vulnerabilities. This should generally work because once the registers are set up in the beginning of main function, the shadowing relationship is kept throughout the execution. However, we have found cases where the nZDC implementation has been careless in selecting its shadow registers and violates the calling convention. For example, there is a case where a special return register is used as a shadow register, and after the register had HASI value set, the value was overwritten by the use of it being a shadow, which resulted in execution failing since the caller never got the return value. A more complex problem that needs more care is in the interaction between the user code compiled with nZDC and the library code compiled without. Usually, even though the library code does not keep the shadow register relationship, this is not a problem because we are copying the shadow registers again after function returns. However, we have encountered cases where this is not enough, for example in exception handling. After the library code handles the exception, the execution resumes wherever the exception is caught, bypassing the copying and causing crashes or failed checks. The more problematic case of library code compatibility is when the library code calls user code. This is actually not that rare. pthread, for example, used all over parsec benchmarks, would call user code. The obvious problem is that, since library code does not keep the shadowing relationship, any checks in the user code would now fail. An easy fix for this would be putting back in the shadow register setup in the beginning of function calls. However, this would break the nZDC feature of input parameter checking. Even with those back in, there are still problems related to callee saved registers. The calling convention defines that some registers are callee saved, and the library code caller would expect those values unchanged after the user code callee returns. However, due to the limited number of registers, some of those are inevitably used as shadow registers, which means that their values would be changed in the user code without ever being stored nor restored. I have gone over 3 main problems we have found with nZDC, which are assuming perfect symmetry between loads and stores when they are not, focusing only on a common special case and missing out on the more general edge cases, and lacking consideration in library and calling convention compatibilities. Please find in our papers more implementation oversights, examples from the spec and parsec benchmarks of the problems, and analysis and proposed fixes and workarounds for them. In the end, we were able to fix enough problems to obtain binaries that can complete error-free executions. 8 out of the 12 spec benchmarks could complete without any error, an additional one with error in the generated output only, and all 6 tested parsec benchmarks could finish without any error. Our performance evaluation result generally matches that was reported in the original nZDC paper, although this was without the transformation for checking conditional branches. This concludes my talk, and thank you for listening.